Good morning.
Good morning.
I'd like to congratulate you all for coming out after being massively plastered at last night's party and probably half dead this morning. It represents the true strength of Kitacon, the people who can fight through the pain and the vomiting. Hello, yes, I'm Mark, or Sparky, it says that here somewhere. Yeah, there. I'm an electronics engineer. I work with the Medical Research Council. I do custom electronics, been doing it for the last 10 years. And then I met my girlfriend, who is big into cosplay and currently asleep. She couldn't work through the pain. I know a lot of people, they like to do cosplay, they like to do electronics on their cosplay, they like lights, sounds, sometimes motors. Those are impressive. But I also know some people have trouble. It's not an easy thing to start on usually, just because people either overestimate what they can do, or they underestimate what they can do. It's not difficult as it seems. So, basically, how to light up your life without setting yourself on fire, because people have. I mean, I did hear a story about someone who put a motorcycle battery in a cosplay. What? I'm not even sure how you'd carry it. Slung between the legs, maybe? Yes, you could wear a backpack, but why? Okay, well, we've got quite a bit, and there is the intermediate panel after this one, if anyone wants to stick around, if I haven't blown your minds already, or if you haven't fallen asleep. Basically, it starts with the math. I'm sorry, I know you don't like math, I don't like math, but it's really easy. It's literally 1 + 1 = 2. That's what I was taught in the beginning, and it's served me really well, the triangles. Voltage, current, resistance, power, and capacity. Capacity doesn't fit in a triangle, sorry. Voltage, current, resistance. I don't know why they use I for current. I blame the French or the Italians. I blame them for most things, but in this case I think I've got justifiable. Basically, if you want to know how much voltage is involved in something, and you know the current and the resistance, 1 times t'other equals the third. Or, in the case of, you want to know the resistance, for example, R, voltage over current. Just remember those triangles, write them down, they're on the internet. That will tell you everything. 90% of the math and electronics involves those triangles.
What should we Google if we need to remember?
Ohm's law, or
Yeah.
voltage resistance triangle. It's literally, it's voltage is current times resistance, resistance equals voltage over current, current equals voltage over resistance. Power, which we'll get to, is the same. It fits in a triangle the same way. Voltage times current equals power. The wattage of your lights. You know you get like a 60-watt bulb. That's the voltage in your mains times the current in the bulb. So you can actually work out the current if for some reason you wanted it. You probably won't be doing electronics with mains electricity. If you are, I will be saying very scathing things at your funerals. Okay, that's just dangerous. Capacity, I'll get to that as well. That's there just so I get all the math up front. There might be like one more equation, but again, it's that level. I don't know if anyone here has run into Kamui Cosplay's Book of Cosplay Lights. It is fantastic. It's a great beginner's guide. It's like, I know it's 5 or 10 quid online, it's PDF. She does a lot better drawings than I do, and she really, gets the details. She explains them well. You can easily remember them. There are 2 errors that I think in her book. They're sort of errors. I'll come to them later. Okay, volts. These were originally animated. Damn PowerPoint 2008. Volts are like water pressure. It lets electricity overcome problems. If you've got something in the way, you pump up the voltage, it gets out of the way. You get enough voltage, the electricity can arc through the air. That's when you get huge up. You don't want those. But when you see that, that's what they've done. They just crank the voltage way up. So Pikachu, he's probably not actually developing that much power. He's just cranking out huge amounts of voltage. Thousands and thousands of volts. To give you an idea, lightning bolts which go hundreds of meters, that's hundreds of thousands of volts. To jump about that far in the air requires 5,000 volts. That's why you don't see arcs very often. Current is like the amount of water you've got available. If you've got 1,000 gallons charging through a pipe, it can do a lot of work, even if it hasn't got much pressure. If you've got a lot of pressure, but just a thimble full of water that's going out all over the place, you're not going to do much work. The current is how much you've got. And the resistance, it's like a tap. You turn off the tap a long way, you get a tiny trickle out. You put a huge great resistor into your electronics, you don't get much current through, you don't get to do much anything, no damage, no work. I actually chose that picture before I realised the back to the Kitacon joke. So, power is watts. You've probably heard of watt is steam engine from history class, and obviously light bulbs, they're all measured in watts. You probably won't need to worry about too much on the basic stuff, but sometimes it'll be like, this component will only handle so many watts. Common resistors that you might use, they're usually about 1/4 watt. At your basic level, you don't have to worry too much, but if you start doing more complex stuff, it becomes an issue because you can accidentally put too much power through a component, it overheats and goes pop. I don't want to scare you with those, they're not dangerous, it's just something to remember again. And then battery capacity. This is something I don't think anyone covers very enough. When you buy a battery, yes, it might do what you want, but it depends how long it'll do what you want. If you're running a costume for an entire day at Expo, say, you need batteries that will last that long unless you want to be changing them every hour. So we'll cover it. We'll cover it all. LEDs. That's the main reason you're here, isn't it? Most people want to put lights on costumes. There are a lot of them. I mean, the standard size that you see in most projects, they're 5mm across. You drill a 5mm hole, you stick the LED in, it fits. Maybe put a little bit of hot glue in there to hold it in place. It's fine. You can get smaller ones that are about 3mm. They're exactly the same as the 5s, just a slightly different size. There's no technical difference. You can also get tiny little ones that essentially stick, they're the size of a grain of rice and they're almost glued onto the circuits. You probably don't want to deal with those just because they're so fiddly. I mean, you can. I've done a few things with them where you literally have to use tweezers and a very fine point of soldering iron or glue, electrically conductive glue. But you take a light, you add a resistor, you put a bit of battery on it, it works. They're the simplest way to do anything on a costume. I'm sure, has anyone seen a person here kind of doing a cosplay with lights? Yes. Yeah? Yeah. Oh, fantastic. It's certainly Kamui's book. It's literally just battery, switch, resistor, light. Makes it a nice entry point if you want to try something. And if something goes wrong, no one gets hurt. You can get much bigger ones. I mean, I've seen 20mm ones. They're the size of buttons. They don't give you more light though. This is the interesting thing. You don't get more light from a bigger LED necessarily. They don't create a lot of heat. This is the other good thing that they're incredibly popular about. If you use a bulb, like an old-fashioned torch, like an overhead light bulb, they put out an awful lot of heat. You will end up being at a point where you can't actually touch the light source because you'll burn yourself. LEDs, you can run all day long. They might be slightly warm, but not in a dangerous way. There's also an issue with directionality. A lot of LEDs, they put out all their light in a beam straight ahead because they assume people are going to look at their LEDs. You have to make sure you get diffused ones that spread the light out in all directions, or else, you know, someone will go, oh, look, that person, they've got an interesting costume. Oh, wait, if I step one step to the side, I'm in the beam of the light and I can see them. It's slightly a problem, but again, if you know what you're doing, if you pick the right LEDs, not an issue. I'm mentioning electroluminescent tape, just as a sidebar. I'm sure you've all seen it. Those dancing guys, they run tape and wire all over their costumes, power it up, and it glows like crazy, but only in the dark. I've seen people do Iron Man cosplays where they've done the chest arc in the center, they've done that with electroluminescent material. It doesn't show up in daylight. Electroluminescent, they're fantastic for parties. You'll see people, you know, go to raves with all the wiring spread all over. It looks fantastic, but if you're going to be going out again, Expo, something like that, it doesn't show up. it needs to be so much brighter to show in daylight. You can get brighter ones now, but they start becoming more expensive and they're still not so vivid that you can actually see them against a bright backdrop. Electricity goes in loops. I'm sure you've run into this before. It's a circuit. You have to connect it at both ends. Basically, it comes out of the pump that is the battery, goes all the way around, through resistors, through lights, back in. It's positive to negative. There's more physics to it than that, but that's all you need to remember. There's a positive side of the battery, the electricity comes out of there, goes through. If you notice, little LED symbol there, it's like an arrow with a bar at the bottom. It's pointing in the direction the electricity flows. As long as you remember that, you won't go wrong. You might have to check online and see which way an LED goes around if you're wiring it, because sometimes it's not easy to tell by looking at them, which is, I think, a bloody stupid idea, but it's not too bad. You can figure it out. Often, if you put a resistor in, you put them in one way, if it doesn't work, just turn it around. You won't damage it by putting it in backwards unless you're using a lot of voltage. There's two ways to wire things up generally, serial and parallel. Serial is, you go one component, next component, back to the beginning. That's fine, nice and simple. You can also do parallel, as in you connect each component in a ladder. So even if one component burns out, the next one will continue working, which is nice for sort of reliability. You accidentally get a duff component somewhere, you've wired it all in, you've glued it all into your costume, you turn the power on, damn, that one doesn't work, but everything else will. If you do serial, unfortunately, one dies, they all die, which I'm guessing would be a bad thing? Probably. It does use more components because you have to give each one its own control resistor, but batteries. There are so many of them out there. You can go from your normal stuff you buy on the shelf to giant great lantern, to the old motorcycle battery. Please don't use those. Please. It hurts my soul. I'm kidding, I don't have one. Duracells. I don't just mean Duracells in the brand, I just mean the standard off-the-shelf batteries you buy. They are the best way to do it. You'll see they've got all sorts of chemistries on them. You'll see written on the side of the battery, alkaline, zinc, carbon, lithium, stuff like that. Alkaline batteries, they're so safe, they're so simple, they're cheap. You don't have to worry about rechargeables or anything like that. Get yourself a little battery box, stick 4 alkaline batteries in, run, if you're running 10 LEDs off that for a costume, or even 20 or 30, they will run for an entire con. They've got a huge amount of power in them. And there is no danger there. Some batteries, you loop around accidentally, you touch 2 wires together, all the electricity is flowing back in on itself and you get a short circuit. If you go back to those triangles, current, resistance, voltage, if you take the resistance down to 0 and the voltage is, say, 5 over 0 doesn't work. 5 over 0.0000, which is what resistance you've got in there, that means current goes through the roof, and current is what creates heat. So you can end up cooking your batteries, cooking your circuits. Yeah, just stick to these guys. They've got something called internal impedance, which I won't go into, but basically they have a safety built into them. If you accidentally short out your wires, they won't catch fire because they've got this internal safety that limits the amount of current you can get out of them. It also means you can't run too big a project off them, because the internal resistance will kill it, but for anything you're likely to do, trust me, it's safe. Okay, you've got all these different types of batteries. NiCads are the old-fashioned ones you probably remember from years ago. They're usually used in like power drills, older power drills, things like that. They're cheap. They are simple. They have a couple of problems. They don't have that internal impedance in them. So if you short something out, they cook. I had a set of batteries in my pocket once, put my keychain in there as well. Suddenly realised my leg was very, very hot, as in I couldn't touch it anymore. It had actually melted the batteries in my pocket. The keychain shorted one out, it dumped all of its energy in like 3 seconds. very bad. So you can use them, but be aware there are safety implications, and you can't get them as much anymore, and they're a pain in the ass to recharge. Lead acids, are you fucking insane? They have lead and acid in the name. That's the motorcycle battery thing. They're cheap. You can buy them. You get all these little block batteries, grey boxes. They say, oh, I'll do 12 volts at 5 amp hours. Yeah, that's great, but you don't want to use them. Just don't. Lithium, they're the new ones. They're all very fancy batteries. They've got huge amounts of power in them. Where a normal battery, you can get like 1.5 volts out of it. These you can get like 3.6 volts, which means you need less batteries, they'll last for longer. This is a little bit more expensive, but you know, there's a trade-off. Also, again, they don't have much in the way of internal impedance, so they can end up putting out too much current in a surge, and if you get a short, heat again, not good. Zinc carbons, they are the cheapest batteries out there pretty much, but they don't give out as much power. So if you only want to run something for a few hours, your batteries have died, someone needs to dash to the shop and get you some. Zinc carbons are fine, but you might run into current issues just because you won't have enough. Alkalines, they're the ones I love. Just off the shelf, buy anywhere, work easily, you can dump a huge amount of power out of them without it being dangerous, and it'll run Cosplay for a day, 2 days, 3 if you're not using many LEDs. Nickel metal hydrides, they're like NiCads. They're slightly more rare because I think the patent has just expired on them. They're pretty good. They're rechargeable. The only thing I will mention, NiCads and nickel metal hydrides, they don't have the full voltage out of them. Normal batteries, like alkaline ones, they have 1.5 volts. So if you put 4 in your battery box and you're running a project of 4 1.5 volt batteries, gives you 6 volts. Batteries over time, they lose voltage. So you start with a 1.5 volt battery, an hour later you might have a 1.4 volt, then a few hours later a 1.3. And eventually, if you've tailored your project to run at, say, the 6 volts you can get out putting 4 of them together, eventually that's going to drop. And you're going to end up, everything's going to be dimming and you're not going to know why. Well, you are if you've watched this, but nickel metal hydrides and NiCads, they start at 1.2 volts. The problem there is you put 4 of those together, that's only 4.8 volts. If you're planning on 5 volts for your project, you're already short. So you have to put an extra battery in. Just be aware. You can use them, but upside downside, they take more space, they don't last as well, essentially. You can make custom batteries. I don't mean by cutting them open, slicing them, taking the bits out. Please don't do that. But you can stack them. If you want, say, a 10.5 volt battery, which is not a common size to buy, you take a 9 volt battery, you put a 1.5 volt battery in serial with it, you get a 10.5 volt battery. Or you take, like I say, 4 1.5s, you put them in sequence, you get a 6 volt battery, which if you only need 5 volts means you've got a little time as the batteries die. The other way you can do it, of course, is you put them in parallel. If you need to use, say, 9 volts, 9 volt batteries, the little power cells you can buy, PP3s, they don't have a lot of juice in them. They sacrifice current to give you voltage. So they won't last as long. I think they do something like 400 to 500 milliamp hours. Currently measured in amps, so a milliamp isn't much, but you'll usually see batteries measured in that. So if you're doing, say, 400 milliamp hours, that's 400 milliamps for an hour, or 1 milliamp for 400 hours. Actually, it's a little complicated by that, but I'll get to it again. But if you stick 2 together, you've got 9 volts at 800 milliamp hours. You stick 3 together, you've got it at 12, you've got 1.2 amp hours. Again, more size, but you get your current, your batteries will last longer. See, this guy, I don't know if any of you remember these. Back when iPods were certainly just becoming a thing, a lot of people, they bought like Altoid tins and they put batteries in them to keep their iPod charged up. The thing is, back then, those iPods, they used, I think it was 12, is it 12 volts? Yeah, about 12 volts to run firewire connections. And you couldn't buy small 12 volt batteries that would work for that job. So this guy, he took two 9-volt batteries to give him that extra oomph because they didn't have much power in them, and he stuck two 1.5-volt batteries on top of it. He gets his 12 volts without having to go with something stupid and huge. And you can do that. It's, if you need a custom voltage, if you've decided I actually need an 8.5 volt battery, you can create that. You don't have to try and find one online or go to some Japanese or Chinese company that will sell you a custom lithium that will last for a week and run in space and give you exactly the voltage you need. You can work around it. Components. You'll find all these diagrams online, and there's always listings of what the components are. They're not scary. Most of them look like what they are. Switches, resistors. It's pretty simple. I mean, I know for a lot of you this is probably actually insulting. You're here because it's basic electronics, not because you want to be treated like children. But just for the people who don't know, this is the various things you've got. Capacitors down the bottom corner, they go in the intermediate class. I just never took them off this slide. Ground right in the centre, that's just another way of saying the negative terminal of the battery. If you go into more advanced electronics, that becomes different. You have to think about that in a different way. But for the moment, if you see ground, it just means negative terminal of battery. Lamps. I've got LEDs there, but you've also got lamps. Lamps are when I talk about bulbs that have filaments in, the old-fashioned, the ones that get hot. They do have one advantage. They put out a lot of light. LEDs, you can see that. You can see LEDs beautifully. They light up, they're lovely and glorious. But again, outside in the full glare of day, sometimes lamps can actually give you a bit more light. Just if you want to do, say, a global end of stuff, where no one's going to be touching it, you can stay well away from it, there you could put a lamp in, you'd actually probably get more light than trying to put LEDs in. When you go buying components online, you'll probably find they come with something called a data sheet. This gives you every single spec of the component, everything. From the emission spectra of the light it puts out, the voltage. It will even have details of how they're shipped on the reel. They're designed for companies who need to know exactly what they're using, but they are your friend. Every time you buy a component, no matter where you get it from, get the data sheet, punch holes in it, and store it in a binder. So when you go back to that component, you can say, this needs so many volts, so much current, and if I do give it too much, more than that, it will go pop. You have to have this data. Otherwise, it's like you're guessing. And if you're guessing, you're going to either underplay your component, you're going to give it too little juice, and you won't get the best out of it, or you give it too much, and the whole thing will go bang. Things don't go hugely bang, but they do enough to make a stink and cause a bit of scare. Or when you're looking online for parts as well, always buy ones that are labelled through-hole or leaded. SMT, surface mount, they're those tiny grain of rice ones I was talking about. They are too small unless you're really experienced to be able to place them easily. You're going to end up dropping them on the floor, not being able to solder them in, or soldering all the way across them and ruining them. Always go for those bigger ones. Yeah, they're slightly bigger, but it's worth avoiding the headache. And tolerances. This is one of the things I was thinking about with Kamui. I love her book. It's good. It really covers the basics. One thing she doesn't mention is tolerance components. Components are made cheaply. They're churned out by the billion by automated factories. They don't set everything to absolutely precise values. If you see a resistor, let's say, that is 1 kilo ohm, resistance measured in ohms, if you go to 1 kilo ohm, it's not actually going to be 1 kilo ohm. It's going to be possibly 5% either side, 10% either side. If it's a cheap component, like 20% either side of that. If you do LEDs, I was going through the Kamu's book, wasn't I? She does a thing where you take 3 LEDs, you stack them in a line, you don't need a resistor, because if it's a 3-volt LED, it will eat 3 volts out of its supply. So if you stack it on top of a 9-volt battery, 3 in a row, 9 volts, you don't need to worry about the resistor in your LED circuit. The problem is, if you then expand that and go to, say, 20 LEDs and try to do it without a resistor, the tolerances add up, and instead of each one eating its own proportion of the voltage, you end up with leftovers. It's, let's see, good example. 10 1.5 LEDs, 1.5 volt LEDs would be 15 volts. But because of their tolerances, they might be actually a 1.3 volt LED, which means at the end, you're going to have something like 2 volts unaccounted for. 2 volts go into the loss resistor, pops. So, yes, you can just stack 3 up and, yeah, but keep an eye out for the tolerances. Most things will come with a tolerance on. They'll say, we are within this and this boundary, but it's not always so easy to understand. Resistors, they resist the flow of energy, like the tap. The tap analogy works well. They're usually measured in ohms, Ohm's law. You usually deal with something around 1,000 ohms, 1 kilo ohm. Why did I put this sheet here? It is completely out of sequence. Back up. Yeah. You'll find this chart online. Simple resistor color code. All resistors have little bands of color on them. They'll tell you exactly what spec the resistor is. You know, first band, say brown. Let's say it's brown, brown, brown. That's 1, that's 110 ohms. Maybe we should do that quicker. Very embarrassing. And then the last band tells you the tolerance. If it's in this case, a silver. Let's say it's a silver band, plus or minus 10%. So you've got a 100 ohm resistor, that means you're actually dealing with a 90 or 110. So it can create problems if you're trying to find precise values. Don't. Always do it so you've got a little slop to work with, or you'll end up overestimating your components or underestimating them. Things will be too bright, too dim. I guess too bright is never a problem, but okay, why? Let's get resistors out of the head. There's so many different types out there. You can buy giant reels of stuff so thick you could hang yourself on it, or so, you know, support. That was bad, sorry about that. Or you can buy stuff so thin it looks like human hair. The human hair stuff is fantastic for cosplay. It's not actually got plastic coating on it, it's got an enamel. You can thread it into a needle and you can actually sew with it. It's not incredibly strong, but it's enough to feed through the parts of a cosplay. And if you want to run voltage off that, you can then hide it beautifully in your stitching and run, attach LEDs to it. It's a beautiful thing to behold when people do that right. Wire is usually measured in either American wire gauge, standard wire gauge, or cross-sectional area. If you see AWG or SWG, they're the gauges. Basically, it's just the bigger the number, the thinner the wire. Not a problem. You want 30 gauge to 40 gauge, that's the human hair sewing thread size wire. Really great for cosplay. If you go somewhere around 28 gauge, 28 to 30, that's good for building projects. You don't want too much because, well, if you go too thick, you can't even bend it. There's a project I was going to show for the intermediate class later. I ended up using the wrong gauge of wire. I underestimated how many wires I needed in it, which means now it's just a solid mass of thick wire jammed in with a crowbar. Okay, not crowbar, but you get the idea. There's two sorts. You can get braided and unbraided, solid core wire. Solid core wire is much easier to work with. You bend it into shape, it stays there. You can push it into holes, you can poke it into circuit boards. Lovely to work with, but it doesn't flex into projects as well. The braided stuff, so much easier to bend around corners, and it doesn't, if you bend it back and forth over time, it doesn't snap. You have to choose. I'd suggest buying a little bit here, buying a little bit there, trying it, see which one you're more comfortable working with. It's very much a matter of preference, and if something is going to be flexed over and over again, you need braided wire. If it's not going to be flexed over and over again, you can get away with the solid core. It depends on what you feel is right for it. Give it a go, try a few out, build your own understanding of how the stuff feels to work with. The thinner it is, the less current it can handle. Again, it's a case of anything you guys do to begin with isn't going to have to worry about current limits on wire. You're not going to be burning out your wires. Just don't go too thin. The hair thickness stuff, It can handle about 800 milliamps without getting too hot. 800 milliamps is 80 10 milliamp LEDs, so you're probably not going to use that many. But if you use high current LEDs, you might end up just drawing a little bit too much through the wire, and then it melts, and you wonder where your circuit's stopped. So again, experiment, see what happens. Soldering, you're going to end up doing it. It's not difficult. It looks a bit scary because you've got a great big hot rod of metal. You plug your soldering line in. You can buy these things anyway. A cheap one, you can buy a cheap soldering line. You don't have to worry about expensive kit for this. If you're just doing a few little things, obviously, better kit, more expensive kit is better generally, but if you only want to do a few LEDs here or there, get yourself a cheap one off the market. It'll be £5–10. You'll get a roll of solder with it. You just heat the thing up, make sure it's in a stand so you don't burn your work surface. Just touch the solder to the tip, it'll melt instantly, and then just smooth it onto the joint. Again, it's very much a practice thing. It took me 3 or 4 years to get a decent soldering style down, but no one's going to see your work, probably, so don't worry too much. You can get both silver and lead solder. You've probably heard of silver solder used for jewellery making, things like that. The lead stuff is the older. It's not used as much anymore because companies are worried about polluting the environment, things like that, but it is better. It flows more easily. The silver stuff tends to corrode the tips of your soldering iron. So stay away from it if you can, unless you're very, very environmentally conscious. The amount you're using, it's not going to become an issue. Obviously don't snort the fumes, but I suspect you're not going to be doing that any more than I do. Taste the brain damage. You can also get these little things called helping hands. They're like little crocodile clips on a stand, very useful for soldering. You clamp your wires in, hold it together, you put a little bit of solder over it, and I'm not running late, am I? No, I'm not. Yeah, clamp them together, a little bit of soldering over them. Do remember to tin your wires when you're soldering. Basically, you take the bare wire, you put a little bit of solder onto it before you try and join it to something else. It makes the surface a little bit more friendly to work with. 2 tinned wires being joined together will be a lot easier to work with than anything else. No, tin your wires. If you're using LEDs, don't hold the soldering iron on the leg of the LED very long. The heat goes up the wire, into the LED, and can cook it from the inside. They're a bit sensitive to that sort of stuff. Just try and only hold your soldering iron on the LED for 2 to 3 seconds max. That should be long enough. The stuff melts pretty easily, but don't hold it there. Oh, why isn't this? Oh, look, it's a butterfly. Oh dear, it's turned black and my expensive LED has dropped off. Probably won't be an expensive LED, but it could be your last one. So. Solid connector conductors on those leaded components I mentioned, if you flex them back and forth over and over again, they will break, unfortunately. So try not to flex them too much. Data sheets, I mentioned these. LEDs, unfortunately you can't see it so well on here. There's a section here called average forward current and DC current. You need to know those for LEDs. The forward current, or DC current, is how much current the LED wants to operate at full power. And down here you've got forward voltage. That's how much voltage the LED needs to turn on. That one is listed as a 1.6 volt LED. You put 1.6 volts across it at 20 milliamps to 30 milliamps, which is the forward current. It will turn on, it will light, that's what you want. If you exceed those, there's a little bit up here, peak forward current, 300 milliamps. It can survive 300 milliamps for a split second. So if you've got sudden surge, it's not going to kill it, but if you try and use that all the time, yeah, pop. The forward voltage, that's how much it eats. Remember I mentioned that it eats a certain amount of power, voltage out of its power supply. You've got a 9 volt battery, you put a 1.6 in there, you're going to have 7.4 volts left. You put another one on, you're going to have 5.8, sorry, terrible at math in my head, and so on and so forth. But if you have less than 1.6 volts available to it, it won't turn on or it'll be very, very dim, just so you know. Yeah, it'll eat it. Then, 6 volts. You've got a 6 volt battery here. So you've got 6 volts all the way along this line here. Great thing about parallel components, you don't have to worry about calculating the voltage each time. It's always there. 6 volts, 6 volts, 6 volts, 6 volts. That means this LED, if we assume it's the one from that we just looked at the data sheet for, that will drop 1.6 volts over there. That will leave you 6 volt battery, so 4.4 volts. Those 4.4 volts have to vanish inside that resistor. So we go back to that VIR triangle we used earlier. We know what the voltage is. It's 4.4 volts. We know what the current is. It's 20 milliamps, because that was on the page before, which gives us about 140 ohms. See, you don't actually need to know these, you can work them out each time. Yeah, there you go, there's the equation for you. I did say there was one more equation. Sorry, I hit it towards the end. It's, you take your supply voltage, you subtract the forward voltage of the LED, 1.6 volts, yeah. 4.4, then it's just, oh there, we're using the DC current, 30 milliamps, 147 ohms. It's really simple, the math isn't, math is always scary, I don't like it, but at least in this occasion it's like 1 + 1 = 2, or you can do it on a calculator, I don't care if you show you're working. Tools. Tools are pretty basic, you know. It's weird, you don't actually use screwdrivers very much. You'd think it's electronics, why are there no screwdrivers? You don't use them, not very often. Soldering iron and stand, because you don't want to be leaving a soldering iron on your desk where you catch your foot around the cable and burn your hand off. Woo! Multimeter, very, very useful. You stick the probes in 2 places, it tells you what the voltage is. You stick it between 2 things, it'll tell you what the current is. So you can actually measure things. You've got a resistor, you don't want to work out the colour code on it, stick it across the multimeter, it'll tell you what the resistance is. Makes your life so much easier. And also if your circuit isn't lighting up the way you want, stick your probes in, it'll tell you what the voltage is. Generally you stick the negative probe on the supply line, the 0 volt supply line at the bottom of the battery, and then everywhere you go, it will tell you the voltage in relation to where the ground, the 0 volt layer is. You put it at the top of the battery, it'll say, oh, you've got 6 volts in your battery. You put it over here, you'll say, oh, you've dropped a volt across your LED, you've actually got 4.4 volts. Just to make sure you've got your levels right. Wire cutters and strippers, obviously very useful. Again, you don't need to buy expensive ones. You can buy expensive ones, and generally they will be better, but you know, a £50 pair of cutters and strippers when you're only doing 3 LEDs for a princess crown, not quite so important unless you're planning on doing a lot more in the future. They can be an investment for you. You'll be reselling them, trust me. Solder braid, this stuff, it's like a wick made out of copper. You put your soldering iron on it, you put it on the joint that you've done wrong, or you've got a solder where you shouldn't have. The solder actually absorbs up into the copper wick, and you can carry it away and clean up your joint. If you're trying to unsolder something that you've put together previously, very useful. There's a little solder sucker thing down here. Same thing, it's like a little plunger. You push the button down, you hold it over the joint, you melt the joint, you press the button, the solder is sucked up into it. Kind of handy. I find them a little bit annoying. Goggles. Solder has something in it called flux, which is like a resin that's used to stop the solder just flowing everywhere and keeps the joint clean. That can spit. You may find while you're soldering, you all of a sudden have a little bit of hot resin, a little bit of hot flux landed on your hand. If you're leaning in close, you want to be wearing goggles, because I do not want to hear you've got flux on your eyeball. I mean, it's not pleasant. It's probably survivable and you probably wouldn't lose your sight, but does anyone really want to play with probably? No. That's the basic. Yeah. I said you don't need screwdrivers. You can have a screwdriver if you want. There's something called chocolate block or connector block. It is not edible. It's essentially a long strip of plastic with copper and brass terminals that go through it and little screws. You put the wires in, you put the wires in the other side, you tighten the screws, and the wires are joined together. If you don't want to solder, or if you want to be able to take the joints out again, it's kind of handy. If you've done one arm for this side of the costume, you've done LEDs for this arm, you've done LEDs for the crown, you've done LEDs for the chest, and you want to join it all together around the back, you can run it into a chocolate block, and then you get to your con, your event, whatever, you put your outfit on, you run all the wires back, and you put them into the chocolate block, do them up. You're in there for however many hours you're going to be in, but it then means at the end, a few twists on a screwdriver, you take all the wires out, and you can dismantle the costume again without having to worry about cutting wires. You'll see electricians use it a lot, often in those circular fittings you see on where there used to be a light fitting or whatever that have been screwed onto the ceiling. They'll have a bit of chocolate block in there, just so it's a nice, easy way to tidy up the wires, screw them into place, and they don't have to worry about them in the future. Extra options. These are really fun. Just stick it in. Beautiful, perfect cut. It'll strip the wire off, it'll take the plastic off, give you a perfect 1 centimetre, 2 centimetre length of wire. I love mine, I have 2 sets. Yes, they were expensive, but they're worth it. I'm not going to push on you. Like I say, if you're going to be doing this stuff, one princess crown every 3 years, you don't have to worry, use a pair of strippers. It might look a bit manky, but you're the only person who's going to know, and I don't care. If you're doing a lot, these will save your fingers. Also component analyzers. I love these. They make my job so much easier. Peak do these Atlas component analyzers. Again, expensive. You're talking 40, 50 quid each. So they're not for someone who's doing it casually. But if you're doing something big, you've got a big project, if you're going to be doing ongoing projects, and you're going to have lots of LEDs and things like that, and you're worried you'll get them mixed up, these things are fantastic. You take the 2 little clips at the end, you attach them onto the component, you press the go button, and it will analyse the component and give you a complete readout of all its specs. It will tell you the forward voltage, it will tell you the current, it will tell you which leg is which. If you've got a component with multiple legs, it will say, oh, the green clip is connected to the anode, the black clip is connected to the cathode, the blue clip is connected to your nuts, what are you doing? I don't see it do that, but if it did, I would be amused. I have a complete set of these for a whole different set of jobs. They are wonderful, but then again, I do this every day. If you're going to get into this for a more complex, or you're going to have boxes of components to go through, they are worth it. Now, is there anything more? Yeah, heat shrink. Heat shrink is great. I love heat shrink. When you've done a soldered joint, that's okay. You've got a little bit of soldered joint there, you've got the silver of the wire, it looks kind of pretty. The trouble is then, if you've got a whole bunch of wires that are soldered together, they can touch each other. Not great. Sometimes they'll just touch each other, the wrong wire will touch, and an LED will light up spontaneously somewhere. That's annoying, but not dangerous. Or we get that short circuit thing I mentioned earlier. The positive and the negative wire touch, everything shorts out, the wires get very hot, possibly melt. What you do, heat shrink everything. You can get that stuff only a millimetre across. You just cut a piece off before you join your wires, you slide it onto the wire, join the wires together, slide the heat shrink across the joint, and run a hot air gun over it. Hairdryer would probably work on a very high setting. Also, paint stripper guns, you can use a cigarette lighter, as long as you don't go too crazy, or just the tip of your soldering iron. That doesn't work as well, but you can do it. Bless you. And that will then shrink down tight over the joint. It covers it up completely. It won't be touching anything. It strengthens the joint a little bit because any pulling force is going to the heat shrink rather than the wire itself. Solder joints can be a bit brittle. They can snap if you bend them too much. Heat shrink, it really helps. The only downside is you then have to, if there's a problem, you have to actually cut the heat shrink off. It's a positive mind, I think it's worth it. Places you can get this stuff. RS components. One called Maplin. Maplin's not as good as it used to be, but you can still get stuff there, and there's a lot of the stores around. Rapid Electronics. They are lovely companies. You can buy pretty much any component you can name, off the shelf and they'll have it shipped to you next day. You can buy a reel of 1,000 LEDs for, you know, 0.2 of a penny each. You'll have to buy it on a roll of 100 or 1,000 LEDs, but you can buy them cheap, very cheap. You can also get all the tools. You can also get engineering materials. If you want brass rod, if you want sheet aluminium, they will ship it to you. I find certainly RS, to a lesser extent one call, they're brilliant for any materials I need. I would prefer to go to them all the time. I can't always, sometimes they don't have it, but 99% of the time they will have what you want. Fritzing, you saw some of the diagrams I had in there. There's a little freeware computer program called Fritzing that allows you to assemble components, electronics on a virtual board, print them off, manipulate them, test them. It's a brilliant little piece of software. Just it makes your life so much easier, just from a design perspective, just to lay things out so that you can get a feel of how things are. You can draw them, but I find often I've like, okay, I filled this corner of the paper and I've got 10 times that to do, but I've somehow got to now drag all the wires out to another part of the paper, which is a pain in the arse. But on computer, so much easier to fiddle with. And finding Kamui, like I say, her book of cosplay lights. I don't think I've done a terrible good job explaining everything in this panel, but her book is a wonderful reference piece. If you can get a copy, I would recommend it. I think it's available on her website, like £5 for the. I'm not affiliated with Kimberly, just so you know. I'm not getting kickbacks. But yeah, I would recommend the book. So, there we go. That's the lot. So, anyone got any questions? I think I might have run a bit quicker than I expected to. You? I've either done such a good job you have no questions, or I've done such a terrible job you're like, oh God, I want to get out of here. I won't ask which, but thank you. Oh, you have a question?
Stuff like flashing lights inside the intermediate session, or is that?
So, the intermediate session, we're going into more complex like flashing lights, sound, that hopefully I'll do a better job explaining that stuff. It's trying to pack several years of degree courses and whatever into a one hour session and then still cover everything. But yes, thank you for your attention. Let's read.
Encore!
That's not yet.